Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 12.6, day 1, entitled The Binomial Theorem. And today we're just going to talk about expanding a binomial to a certain power, and then we're going to talk about binomial coefficients as well. Now you know that when you have two terms that are added or subtracted together, that's called a binomial. And it's pretty easy to take that binomial and raise it to some power. Although when the power gets really, really big, then multiplying that all out becomes really tedious because you have to keep doing distribution and combining like terms. So in this section, we're going to show you a shortcut for how you can take a binomial to some really big power and get the final polynomial. Okay, so that's what we're going to refer to as expanding that binomial. Now, I want you to look at this pattern here. So I have a plus b to the first power. Well, that's just going to be a plus b. And then a plus b squared. You start with a squared, and then 2ab, and then b squared. And that's traditional double distribution or foiling. So that would be a perfect square trinomial. So you know how to distribute and factor that. Okay, this next one, a plus b to the third, we have a to the third, and then a to the second, and then a, and then our last term here is b to the third, and then we go backwards to b squared, and b, and then no b. And then notice that our first term is 1, and our middle terms are 3 and 3, and then our last term here starts with a 1. Okay, and as we keep looking here, you can see that the a term for a plus b to the fourth power, the a term that leads, it has a 4, and then there's a to the third, and then a squared, and then a to the first, and then b to the fourth is at the end, and then if we go backwards, we get a third, and then a squared, and then just the b, and then there's no b. So these are some of the patterns that we'll talk more about in class, but these are some of the observations that hopefully you make. Okay, and notice that there are also n plus 1 terms. So that means that if you have n as a power here of 1, you're going to have 2 terms. If n, your exponent here, is 2, then you end up with 3 terms altogether. Here we have 3, but you end up with 4 terms. So that's an observation. And we notice that the first term begins with a to the n, and the last term is b to the n. We notice that the exponents decrease by 1 for the a terms, and that the exponents of b increase by 1, or they kind of decrease going backwards. And then the sum of the exponents of a and b is always going to be n. So let's take a look at that. So here the sum of my exponents. Here I have to have a 2 as my n value. So the sum of the exponents of a and b. Okay, so my a term and my b term will be that in any single term. Oh, okay. So a here is to the first power, b is to the first power. Here a is to the second. Here if I add them, 1 plus 1 is 2, and that one is 2, and then 3. So I have a to the third, and then 2 plus 1 is 3, 1 plus 2 is 3, has a 3. So any individual term has a sum of n. Okay. So that's not really, oh, I guess it does say sum there. The sum of the exponents is n. Okay. So these are just some observations that we'll talk about in class, but these are the observations that are going to help us develop a pattern or a rule, kind of a trick for how we can expand binomials. So here again, this is where it talks about the exponents are decreasing for a. So we have 5, 4, 3, 2, 1. And then they're increasing for b. Notice that the first term doesn't have b though. The second term has b to the first, and then you go to the second, to the third, to the fourth, to the fifth. And the other way to think about it, which I think can be helpful, is that your very last term has b to the n power. So in this case it's 5, and then it goes backwards, 4, 3, 2, 1, and then you have none. Okay. So again, these are observations that are going to help us come up with the rule for expanding binomials. And when we're writing a big polynomial like a plus b to the eighth, when we're writing out the answer here for that, we now know the pattern for our variables and their exponents. We'd have a to the eighth, and then seventh, sixth, fifth, fourth, third, second, first, and then no a. And then this last term will have b to the eighth, and then 7, 6, 5, 4, 3, 2, 1, and then no b. But how do we come up with the coefficients? That's what we need to take a look at. And they showed it in the little chart that they had. Was it this one? Nope. Where did it go? Here. You can kind of see it here. The coefficients, let me write it in, are 1 and 1 here. Then the coefficients are 1, 2, 1. And the coefficients are 1, 3, 3, 1. And then 1, 4, 6, 4, 1. So the outside numbers are always going to have the 1s. And then this middle number here you get by adding these two together. So if I add the 1 and the 2, I get the 3. If I add the 2 and the 1, I get this 3. So a better way to look at this is if we kind of line it up a little bit neater right here. Okay? So my first term had a coefficient that was 1 and 1. And if we have a plus b to the 0, that's just 1. So that's kind of the top of the pyramid here, the top of the triangle. And then 1 plus 1 gets me the 2's. Okay, so this one and this one, if I add them together, I get the 2. This one and this 2, if I add them together, I get the 3. That 2 and that 1, if I add it together, I get the 3. And so on and so on. So the 1 plus the 2 is the 3, the 3 plus the 1 is the 4, the 4 plus the 6 is the 10. Okay, so that's how we can get every single row for any binomial expansion. Okay. And this is all related to Pascal's triangle. Okay. Pascal is a famous mathematician, and he came up with this pattern. Okay. And that tells us that every entry is the sum of the two entries diagonally above it. So that means, though, that this type of expansion is recursive because we need the previous row in order to come up with the next row. And we've talked about recursive functions earlier in this chapter as well. So we're going to use this property of Pascal's triangle to help us rewrite these binomial expansions, or write out these binomial expansions. Okay, so if we have a plus b to the fifth, there's that row. And again, we got that by adding together the previous diagonal a plus b to the fourth numbers. And then if we take the 1 plus the 5, we get the 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 and 5 is 15. 5 and 1 is 6. And it always ends with a 1 and a 1 on the outside edges. Okay. So now that we understand the decreasing rule for the exponents, and now we know how to come up with the diagonal addition so we get our row of our coefficients to fill in too, we can put those together and then we'll have our fully expanded binomials. Okay. And that just talks about stuff that we've already discussed. So basically what you have to remember then is that the coefficient is the sum of the coefficients of the two terms that are diagonally above it. Now this is useful when you have small numbers that you're working with, when you have a plus b to a small power for an exponent. So if we have a plus b to the seventh, that's not too terrible. You could write out the first 7 rows of Pascal's triangle. But when you're getting into much bigger exponents, then it becomes a little tedious. So I'll show you another shortcut for that. But let's take a look at our expansion here for a plus b to the seventh. So let's talk about our a's and our b's first. I'm going to have a to the seventh. And then I'm going to leave a little bit of room in between my addition here. I'm going to have a to the sixth, and then I'll have something else. A to the fifth, something else. A to the fourth, a to the third, a squared, and then a, and then I'm going to have that term that has no a, and this is where my b to the 7th will be. And then I'll have b to the 6th, b to the 5th, b to the 4th, b to the 3rd, b squared, b to the 1st, and then no b. So that's the way I like to fill it in. I like to start with my first term and go all the way from left to right, and then start with my second term and go all the way from the right to the left. And remember to do that double check that every degree has to add up to 7. So here I only have one term and it's a 7. Here 6 and 1 gets me a 7. 5 and 2 is a 7. 4 and 3 is a 7. So the sum of your exponents has to equal that n value. Okay. Now the other thing we have to fill in is our coefficients in front of these terms. So we could write out all 7 rows of Pascal's triangle, but it was written out here previously in the notes. Okay, so if we wrote out the first, second, third, fourth, fifth, and then the 6th and the 7th rows, this is what we would end up with. Okay, so these numbers here, these are going to be our coefficients in front of our terms. So that means I'm going to have 1 a to the 7th, and 7 a to the 6th b, and then 21 a to the 5th b squared, 35 a to the 4th b to the 3rd, and then another 35 a to the 3rd b to the 4th, and then 21. And notice here, since I don't really have any middle term, I'm repeating this 35 twice, and now I'm going to go back to all these other numbers. So I'll have a 21 a squared b to the 5th, and then I'll have a 7 a b to the 6th, and then I have my 1 again, b to the 7th. Okay, so this is my final answer here, this last row that I wrote out. That would be the expansion of a plus b to the 7th power. Okay, so you're going to see some problems like that on your homework where you have to expand a binomial. So use that pattern for the descending values of the exponents and check your sums on the exponents as well. And then use the Pascal's triangle so that you can come up with the coefficients in front of each term. Now this can become more complicated when you have bigger exponents, and it can also become more complicated when you have terms that aren't just a and b. Like we might have 2x squared as the first term and 10y to the 3rd as the second term in our binomial. So we'll take a look at that in the next section of notes. Okay, but let's talk about what happens when that expansion that they want you to do and coming up with those lead coefficients becomes more and more complicated. Okay, so when we're trying to come up with those binomial coefficients, this is where it can be a little tricky. So Pascal's triangle is really useful, but when we get to large values of n, then it's not as useful. And like I said earlier, Pascal's triangle is recursive. You need the previous rows to come up with the next row. Okay? So if we need to find something that's in the 100th row of Pascal's triangle, that means I'd need the 99 rows before it. And that's a lot to write out, and it takes a lot of time. And if you make a mistake somewhere, then the rest of the triangle is messed up. Okay? Now, we could look for it online too, obviously. Okay? But we need a different way. We need to figure out how to do this. And how we're going to do this is with something that's called factorial. And we're going to talk about this more in the next chapter as well. In chapter 14, when we're dealing with statistics, you do a lot of factorials. And factorials in math are just a cool way to do multiplication. And it's a shorthand notation as well. It's a shortened way to write something. So what this means is when you have a number with the exclamation point, that exclamation point is the factorial, and it means you're going to take that number times every other number that comes after it. So if I had 5 factorial, that's 5 times 4 times 3 times 2 times 1. So the way it's written here shows it going from 1 to 2 to 3 all the way up to n. Okay? But when we're actually using numbers for the value of n, we'll write it this way in a descending order. Okay? And your calculator can do this. You have an exclamation point on your calculator. And remember that when you have 0 factorial, that's always 1, okay? Because it's kind of like dividing a number by itself. So how we use the factorials then to come up with a binomial coefficient is with this rule right here. And this is our shorthand notation. We're going to have an n value and an r value. Okay? And n and r are going to be the non-negative integers. Okay? R has to be less than or equal to n, so they can be the same. Okay? Um, but n has to be bigger, so just think that it's on the top. It has to be bigger. Okay? And n is going to be this first number on the top, and then r is going to be the number on the bottom. Okay? So we'll have n factorial over r factorial times the difference of n and r factorial. And basically what this is a rule for combinations, and we're going to talk about combinations in the next chapter, chapter 14, when we do statistics, okay? But for now, just know that n and r are those numbers that we're plugging into this notation here, and this is going to help us come up with the binomial coefficients, okay? So let's just practice for a moment coming up with those values, and then we'll put it all back together in Pascal's triangle. Okay. Now, your calculator can do this as well, but I want to show it to you with the formula first. Okay. So here I have n over 4, and I'm not really going to be a stickler on how you read this. It's really a combination. Okay. But we've got our binomial expansion here, our binomial coefficient of 9 and 4. So that means I'm going to take 9 factorial over 4 factorial times 9 minus 4 factorial. Now 9 factorial, I'm going to write this all out for the first time just so you can see what it really means and what's really going on here. But this can be a little tedious if you have really big numbers. So we have 9, 8, 7, 6, 5, 4, 3, 2, 1. So that's what 9 factorial means. 4 factorial is going to be 4 times 3 times 2 times 1. And then 9 minus 4 is 5, so then I'm going to have 5 times 4 times 3 times 2 times 1, because I'll have 5 factorial. Okay? So now I can cancel some stuff out here. I can cancel out 5, 4, 3, 2, 1 and 5, 4, 3, 2, 1. Okay? And then there's a couple different ways that you could cancel the numbers here. You could cancel the 4 into the 8. You could cancel the 4 and the 2 to get rid of the 8. And then the 3 goes into the 6 2 times, or you could put the 3 into the 9 3 times, however you want. Okay? But then we just have to multiply across the numerator and the denominator. Now the only thing that's going to be left in the denominator is 1. And when I multiply across the numerator, I'll have 9 times 7 times 2, and that should get me 126. Okay? And again, I'll relay what this means when we're dealing with Pascal's triangle in a moment. Okay? But for now, we're just figuring out how to calculate these binomial coefficients. Now for part B, this is where it becomes way more useful when you've got really huge numbers like this. I've got 100 over 3. So that means that I would want 100 factorial over 3 factorial times, and then it would be 100 minus 3. So that would be 97 factorial. Now, I'm not going to write out 100 times 99 times 98, etc., all the way on to 1. Okay? But I have to know that that's what that means, because here in the denominator I've got 97 times 96 times 95 and so on and so on. So basically from 97 on, everything in the denominator and the numerator is going to cancel. So that means in my numerator I have 100 and I have 99 and I have 98, and then everything from 97 on cancels. But I still have the 3 and the 2 and the 1. And then again, I can cancel a little bit more. I could put 3 into 99 33 times. I could do 2 into 150 times. So I can cancel a little bit more. But the main thing to recognize here is that from 97 on, I'm canceling everything out from the denominator and the numerator. So now again, I'd have to take 50 times 33 times 98. And that's going to be a really big number, 161,700. So I don't want to do the 100th row of Pascal's triangle because I'm going to get numbers that are this big. Okay, so now let's take a look at our last one here. We've got 100 over 97, so that means I would have 100 factorial over 97 factorial times 100 minus 97, that's 3 factorial. Hey, that's exactly what I had over here for this other one, okay, for part B. Now, if you didn't recognize that, you could work through this again. Again, the 100 factorial is 100 times 99 times 98. The 97 is 97 times 96 times 95. So all the 97s are going to cancel. So again, I would end up with 100 times 99. Oops, 99 times 98. And then over 3 times 2 times 1. So again, I'm going to get the 161,700. Now these are going to be the same because these are in the same row of Pascal's triangle. It's just a number that's in the third spot and a number that's in the 97th spot. So they're like at opposite ends of that same row in Pascal's triangle. Okay, so that is all due to Pascal's triangle. That's why these values end up being the same. Now, on your calculator, if you want to do this, you can go to, you have to enter this top number first. So let me write these steps down. We'll talk about this in class as well. But you enter your top number. So you would enter number 9. And then you're going to go to the math menu. And you're going to arrow over to the probability menu. And then you're going to select option 3, which looks like a P and then a capital C and then an N. And that's the notation for a combination. And then you want to enter the bottom number. And then hit enter. And it will evaluate it for you. Okay. So your calculator is programmed to do combinations and permutations. Permutations have the P, and again, we'll talk about those in the future. But for now, just pick option 3 with the C for combination, because that's really what this is. You're doing a combination. Okay. All right, so when we're dealing with Pascal's triangle, this is how we're going to use these numbers. And we'll talk about more of this in the next part of these notes, in the day 2 of the notes. But this is just going to kind of set up how we would use the 5th row of Pascal's triangle. Okay, so if I have a plus b to the 5th, then I would have a 5 over a 0. So that's kind of like what my exponents are. I'd have a to the 5th. Okay. So I'm going to have that 5 across the top. And then the bottom is like what the exponent would be for the b. You could kind of think of it that way. It's going to be a 0, 1, 2, 3, 4, and then 5. Okay, and so it's kind of like you know that you have to have 5 terms, and well, you're going to have 6 terms. You're going to have n plus 1 terms, but it's in the 5th row, and then you want to make sure that the bottom has a 0, and then it increases up so that it's the same number. So if we had a plus b to the 10th, we'd be in the 10th row. Okay, so we'd have 10, 9, 8, 7, and so on and so on. And then the bottom we would have 0, 1, 2, 3, 4, 5, and so on and so on. So the last number should line up, and the beginning will have the 5 and the 0, or the 10 and the 0, or whatever. Okay? So these numbers, then when we evaluate them, give us 1, 5, 10, 10, 5, and 1. And that's the 5th row of Pascal's triangle, which is right here. Okay, there's our 5th row. So our 4th row, 3rd row, 2nd row, 1st row, and then that's just the 1 in the top of the pyramid. Okay, so it's kind of like telling you what row you're in and then what space you're on, sort of. Okay, so you've got n here in the bottom, this is the pattern that really describes it. Okay. You're going to have n for your number of your exponent. That's the row that you're in. And then you start with 0, and then you go to 1, 2, 3, and so on and so on. And at the end, they have to match. Okay, so if you're on the 25th row, it'd be 25 over 25. Okay, so like I said, we'll see more of that in the next day's notes when we get to them. But for now, just know that that's where we're going. Okay, we're using these binomial coefficients so that we can find bigger values in bigger rows of Pascal's triangle. So take a look at these homework problems. Make sure you remember the rules for the increasing and decreasing pattern in the exponents. Use your binomial coefficients, use your calculator, and work through these problems. And if you have any questions, come on in and see me before school.